So for this first one, what do we have to do first? Subtract the 7s from both sides. So 3x equals 18, and then divide by 3. So x equals 6. Over here, what do we have to do first? We have to combine the 2x and the 5x. They're on the same side, so we can just combine them together, which makes 7x minus 1. And now we can add the 1, yes. Remember, we always have to get it down so the variable, before we can actually start the solving, start taking it apart, we have to combine and simplify so that the variable only appears once. So now that we do, now we can, like you said, add 1. So 7x equals 35, and then divide by 7. So x equals 5. Any questions? Okay. So today I want to do a little bit of review of integers. Make sure you got those down. Then I want to use those in our algebraic numbers to see how that's going to work, how well you remember them. So, negative 19 plus 32. I'll give you a second to see what you come up with. Now, what I'm always thinking in my mind, starting at 0, negative 19 goes this way. Positive 32 goes the same or the opposite? Opposite. Shorter or longer? Longer. So it goes past 0, putting us in the positives. The arrows, the vectors go opposite directions. So that means we're the difference between their lengths. So 32 minus 19 is 13. So that is a positive 13 is that result. So the addition isn't bad. It's just a matter of doing the vectors. Where it gets tricky is the subtraction. Like negative 43 minus 26. And the way we handled that was we don't subtract. We turn it into adding the opposite. So negative 43 minus 26 becomes negative 43 plus negative 26. So now we've got negative 43 and negative 26. Both go the same direction. So we know the answer is negative, and we're adding the absolute values to the same direction. So 69, negative 69. Or we might have 51 minus a negative 33. Again, the first number never changes. The operation, the subtraction, division, whatever it is we're working with, works on the number that comes after it. So the 51 doesn't change. The subtraction works on the number after it. So it becomes plus, adding the opposite of negative 33, which is positive 33. So it's just 51 plus 33, which is 84. Now, the reason I'm stressing that, going over that again, is because in our algebraic numbers, we have to deal with that a lot. And that's the most difficult part of dealing with the algebraic numbers usually is dealing with the negatives. Our algebraic numbers are actually very, very similar to our whole numbers. If we look at our place value, this is the 10 to the 0 place, or the 1's place. 10 to the 1, or the 10's place. 10 squared, or 100's place. 10 to the 3rd, or 1,000's. 10 to the 4th, or 10,000's. 10 to the 5th, or 100,000's, and so on. In fact, our decimals are even defined as negative powers of 10. When we wrote out a number in expanded form, like 572, we wrote it out as 500s and 7 10s and 2 1s. But we can shorten that up using the powers of 10 like that as just 5 times 10 squared instead of 500s, plus 7 times 10 to the 1, or just 10, plus 2 times 10 to the 0, or 2 times 1 is just 2. We just leave it as 2. We don't have to put a label on that. If we see our numbers written out in expanded form like that, it makes our algebraic numbers make a lot more sense. An algebraic number might look like this. So you can see here the similarities. This is the x squared digit compared to the 10 squared digit. This is the x digit compared to the 10's digit. The 1's digit and the 1's digit. Or the 10 to the 0 and the x to the 0, if you want to think of it that way. Anything to the power of 0 is 1. So whether it's 10 to the 0 or x to the 0 or whatever, it's still the 1's place, the 1's digit. And with this analogy in mind, the way we work with these algebraic numbers is going to be exactly like the way we work with whole numbers. So if I have 3x squared plus 8x plus 4, and I want to add to it 2x squared plus 5x plus 3. Now the parentheses here are not an enclosing symbol. There are 2 uses of parentheses. One is an enclosing symbol telling us we have to do something there first. The second use, like we saw with our negatives, is just a separator, to separate that part of the number off to show that it is one complete thing in itself. Like when we were using the negatives, it showed us that as a negative, not subtraction. Same thing here. There's nothing to do inside either of those sets of parentheses. They're just separating out the numbers. To add these, we're going to do it just like we would with whole numbers. We're going to write down the first one, 3x squared plus 8x plus 4. Then we're going to write down the second one, making sure we line up the place values. 2x squared goes under the 3x squared. 5x goes under the 8x. 3 goes under the 4. The 1's go with the 1's. And we are adding these numbers. So now, there are some very, very small differences here that actually make it almost easier. We're going to add the columns. 4 plus 3 is 7. So it's a positive 7, so put a plus in front of it. 8x plus 5x is 13x. With algebraic numbers, we don't have to carry. We can have more than one digit in that place value. 3x squared and 2x squared, 5x squared. A lot of you are probably taught a shortcut where you just take out the parentheses and combine like terms, which works, but this is actually what's going on. You're actually doing a long addition. So we've seen a couple of differences between our algebraic numbers and our whole numbers already. One is the algebraic numbers are always written out in long form. They always have the place values in there. The second is we don't carry with our algebraic numbers. We can have a 2-digit number in that place value. The third difference is probably the most critical difference, and that deals with negatives. If I have a negative 293, when I'm dealing with integers or whole numbers, either every digit is positive or every digit is negative. Negative 293, that is a negative 200s, and a negative 9 tens, and a negative 3 ones. Every digit of that has to be negative. In an algebraic number, I can have 3x squared minus 5x plus 7. Each digit can be positive or negative on its own. This is a positive 3x squared, but it's a negative 5x, a positive 7 ones. So when I'm adding or subtracting or whatever with these, that can be a little bit of a complication. So 5x squared minus 9x plus 2 plus 3x squared plus 7x minus 8. So I'm going to line these up. 5x squared minus 9x plus 2. Line up the x squareds. Line up the x's. Line up the 1s. And we are adding down the columns. Now again, this operator here works with what comes after it. So that's saying this is a negative 9x. Here that's saying this is a negative 8 ones, or negative 8. So when I go to add, this is 2 plus a negative 8. So positive 2 and a negative 8 makes negative 6. This is negative 9 plus 7. So negative 9, positive 7, negative 2x. 5x squared plus 3x squared, 8x squared. Any questions? Okay. Where the complications come in is when we have subtraction. So I purposely had all the digits be positive here on the first example. Doesn't mean all the results are going to be positive, but all the digits we're going to work with are positive. To start out with. And we are now subtracting down the columns. So here we have 3 minus 9. Negative 6. Very good. 2x minus, or 7x minus 2x. 5x. It's a positive, so I'm going to put a plus in front of it. 3x squared minus 5x squared. What's 3 minus 5? Negative 2x squared. So we get negative 2x squared plus 5x minus 6. Well, where I really start to lose people, where people start to struggle, is we start subtracting with negative digits in there. So we might have 2x squared minus 9x plus 3 minus 7x squared plus 2x minus 11. So we write this out, 2x squared minus 9x plus 3, 7x squared plus 2x minus 11. And we are now subtracting down each column. I'm going to warn you before we get started, be very, very careful with these. This is 3 minus a negative 11. I usually write it off to the side so I make sure I'm seeing it right. That is 3 minus a negative 11. Now remember, that becomes 3 plus positive 11. Okay? So 3 plus 11 is 14. So it's positive 14 plus 14. Here we have negative 9 minus 2. So again, I'm going to write it over here. Negative 9 minus 2. I'm going to change that into negative 9 plus a negative 2. So negative 9, negative 2, that makes negative 11x. And 2x squared minus 7x squared was 2 minus 7. Negative 5. Good. What do you think? Like I said, it's generally the negatives that give people problems here. I'm going to have you try one in your notes, see how you guys do. Give that one a shot in your notes. See if you may. So we line this up. We are subtracting down the columns. Negative 3 minus negative 13. What'd you get? positive 10. Negative 3 minus a negative 13 becomes negative 3 plus a positive 13. So negative 3 plus 13 is positive 10. Negative 7 minus 9. Negative 16x. Good. Negative 7 minus 9 is negative 7 plus a negative 9. So negative 7, negative 9 is negative 16. 5 minus negative 2. Positive 7x squared. Good. 5 minus a negative 2 becomes just 5 plus 2. Or 7. So as you can see, the real trick here is just dealing with the negatives. So then our next step. We've done some of these before. Let's see how you do. See if you recall how to do these. Try that one in your notes. See if you get it. Okay, so we see parentheses, which tells us we have to do something there first. We're going to work left to right, so we're going to start with this parentheses. Nothing to do inside that parentheses, so we have to multiply the 3x. 3x times 5x to the third for 4. Perfect. 15x to the 4. 3x times a negative 7x. Negative 21x squared. Good. Over here, this set of parentheses. Again, nothing to do inside of them. So we're going to multiply by, it's a negative 5x squared. Don't miss the negative there. So negative 5x squared times 2x squared. Negative 10x to the fourth. Negative 5x squared times 3. Negative 15x squared. Good. What can we combine? Like terms. So give me the first set. Perfect. 15x to the fourth and the negative 10x to the fourth combine to make 5x to the fourth. Negative 21x squared and negative 15x squared make negative 36x squared. The tough part in these problems is remembering how to deal with the powers. Up here, we were multiplying. That's why you added the power. That's why I did 1 plus 3 makes 4. Or 2 plus 2 makes 4. When we're multiplying, we combine the names. We combine the powers. But down here, when we're just combining like terms, we're just adding or subtracting, we keep the same name. We can only combine things that have the same name, and we keep the same name. Okay, so it sounds like you guys are doing pretty well with the algebraic numbers. Let's do a few more examples of word problems to see how you guys are holding up with those. We'll see how long my voice holds out for the day, too. So, let's say that in a month where they sell 56 cars, Pat sells 3 times. Oops. I'll put all the letters in the words. 3 times. Bless you. As many as Sam. How many did each sell? So here we have 2 things we're looking at. We're looking at the number Pat sells, the number Sam sells. can't have two separate variables. I can't call one x and one y because then I don't know how to solve the equation. So I have to figure out how to express both of them in terms of the same variable. So I look through the problem, is one of those amounts expressed in terms of the other? Pat sells 3 times as many as Sam. So yes, one is referenced off the other, or expressed in terms of the other. So which one do I want to let be x? The one that's being referenced, right? So Sam. So the number that Sam sells is x. So if I know that Sam sells x cars, how do I express the number that Pat sells? 3 times. 3 times x, so 3x. Those two numbers, 3x and x, add up to the total of 56. So 3x plus x equals 56. Now when you see an x like that by itself, there are some, we call them hidden ones or invisible ones, whatever you want to call them. This is really 1x. We just don't write the 1. Kind of like having an inch. We sometimes just say, instead of 1 inch, we just say an inch. It's also to the power of 1 that we went over when we did our powers. In this case, that doesn't really matter because it's just x and x. So now to solve this, our first step is to combine the ones, the x's. 3x and 1x make 4x. So 4x equals 56. And we solve by dividing by 4. So x equals 14. Okay? Now, we are not done yet. A lot of people, they solve the equation and they're satisfied. It feels good to get that far. We wrote an equation, we solved it, we're good. But you have to remember to ask the question. Answer the question. The question was, how many did each sell? Well, x is how many Sam sold. So Sam sold 14. But we still have to answer how many did Pat sell. Pat sold 3x. So 3 times 14 is 42. So Pat sold 42. What's that? Cars, yeah. This is an example of a type of question where we have one amount, we'll call it amount A, plus another amount, we'll call it amount B, add up to give us a total amount. That's one type of question that we can deal with. We have other questions where amount A minus amount B might give us a difference. We also have questions where the two amounts have to equal each other. Obviously, there's usually something else involved with each amount in those cases. So let's look at some other examples. For example, let's say that Chris sells, yeah, change it up a little bit. Can't go 3 times again. Chris sells 4 times as many cars. We're sticking with car sales. As Stacy. If Chris sold 33 more cars. Again, how many did each sell? Well, the number Chris sold the number that Stacy sold. Can one be expressed in terms of the other? Okay, so which one do I want to let be x? Stacy. Chris would then be 4 times that, or 4x. What's my equation going to be now? There's 2 ways I can write this. Chris sold 33 more. In other words, Chris minus Stacy equals 33. Or I could write it as Chris equals Stacy plus 33. Either way is fine. Either way works. This way is just a little simpler to solve. So Chris is 4x minus Stacy is x equals the difference of 33. What is 4x minus x? 3x. Good. You think of that as 1x. So 4 minus 1 is 3. So that is 3x equals 33. And then divided by 3. X equals 11. So now what? So that tells us Stacy sold 11 cars. Chris was 4x, or 4 times 11 is 44. So Chris sold 44 cars. Any questions? Okay. Now let's look at something just a touch more complex. Let's say that Pete sells t-shirts for $8 and hats for $4 each. Pete sells 3 times as many t-shirts as hats for a total of, well, what do I do here? Let's do $749. Actually, let me be careful here. Make sure it works out. $476 will work better. So for a total of $476, how many of each did he sell? I'm just going to put how many of each again. There's an extra level of complexity in this problem. So we're going to look at the t-shirts and the hats here. And the first thing we're going to look at is the number sold. Just like before, one is referenced off the other. One can be defined in terms of the other. That's done right here. So X will be hats. T-shirts will be 3X again. 3 times as many hats. But we're not given the total number of items sold. It's not 3X plus X that equals anything. We're given the total dollars. So we need to find the dollar amounts for each item. The dollar amounts for an item is equal to the price times the number sold. So here, for t-shirts, what's the price? $8 times we sold 3X of them. Does that make sense? So the total dollars from t-shirts is 8 times 3x, or 24x. How about hats? What's the price for a hat? $4. How many did we sell? X. Well, 4 times x is just 4x. Good. That's the dollars for hats. Those two dollar amounts, 24x plus 4x, add up to the total dollar amount of $476. Now what do we do to solve this? Add late terms. 24x and 4x make 28x equals 476. And then divide by 28. X equals 17. Now again, we're not done. That's the number of hats sold. Because X equals 17. T-shirts will be 3 times 17, or 51 t-shirts. Any questions? So there's an extra level there that comes into play. Now we're going to look at another problem here. Has that same extra level. Actually, it's going to be the same problem. We're just going to define it in a slightly different way. So Pete still sells t-shirts for $8 and hats for $4. However, this time Pete sells 68 items for a total of $476. Again, how many of each did Pete sell? So to define this one, we still got t-shirts and hats. And we still have to define the number sold. Now here, one is not referenced off of the other, but there is a relationship between them that is given. Can anybody pick out what it is? There you go. Total of 68 items. T-shirts plus hats has to equal 68. Now, I can't have two variables. I can't do t plus h equals 68. I mean, I could, but that would require us to get into a system of equations, which we're not ready to get into yet. That'd be two different equations with two variables. So I would need to figure out a way to express this as one variable. So I'm just going to pick one, t-shirts or hats, doesn't matter which, to be my variable. Which one do you guys want me to choose? T-shirts. So let the number of t-shirts sold be X. How many hats are sold then? Well, there's 68 total items. Let's say I tell you that we sell 40 t-shirts. How many hats were sold? 28. How'd you get 28? 68 minus 40. Well, we don't know that there was 40 t-shirts, but there were X t-shirts. So instead of 68 minus 40, 68 minus X is the number of hats sold. So now we need to find our dollars, the dollar amount for each item. The price per t-shirt was $8 times we sold X, so that's 8X. Price per hat was $4 per hat. Times the number sold is the 68 minus X. So we're going to combine those here. 4 times 68 is 272. 4 times negative x, negative 4x. Now these two numbers have to add up to 476. So 8x plus 272x minus 4x equals $476. What's the first thing we have to do here now? Combine the 8x and negative 4x, which is 4x. We still have the positive 272 equals 476. And then, yeah, subtract the 272. So 4x equals 204. And then divide by 4. So x equals 51. So let's go back and answer the question. X is 51. There's 51 t-shirts sold. 68 minus x becomes 68 minus 51, or 17 hats sold. So you see, it's the same problem. Same answer, just a different way of phrasing it. Now you might ask, would it make a difference if I'd let x be the number of hats? No, it wouldn't have. The equation would have looked a little different, but we would have solved it, came out with the same numbers. Let me show you what I mean. If I let x be the number of hats sold, the number of t-shirts sold would have then been 68 minus x, right? So the dollars would have been 8 times 68 minus x, which is, what, 544 minus 8x. 8 times 68 is 544. 8 minus negative x is minus 8x. This would have been just 4x for the hats. $544 minus 8x plus 4x, but it's still equal to 476. We would still have to combine our x's. Now this time, however, negative 8 and positive 4 makes a negative 4x. We would subtract the 544. Negative 4x equals a negative, 4x, not 46, equals a negative 68, and we divide by negative 4. X equals 17. So if we look back up here, 17 hats, 68 minus 17, or 51 t-shirts. So it comes out the same. It's just the process looks a little different. So the key to these word problems is organization. A lot of people just start writing equations for them, and that works. You can get the equation correct, you can solve the equation, but I see in some of these more complex word problems, you solve the equation, you get a number for x, and you forgot what x meant in the first place. You know, here, as soon as I solved the equation, I got that x equals 17. Looking back up here tells me, oh, x was the number of hats. So I know 17 is the number of hats. So take a little bit of time, organize yourself. I'm sure if you had a high school algebra class, they preach that you define your variable. I'm not one to often repeat what a high school teacher says, but that's one thing that is very important. Make sure before you write your equation, you have somewhere written down what x equals, or what whatever letter you're using for your variable. What does that mean? What does it stand for? Is it the number of items sold? Is it the dollar amount? Is it the hats? Is it the t-shirts? What does it stand for? Okay, it's about 5 minutes early, but my voice is giving out. So that is really all the material we have for this week anyway. Don't forget, there is that quiz that is due tonight at 11:59 p.m. tonight. And then there is that new homework. It is due Monday. Sounds like everybody's got this crud coming down with it, huh?